Ah, Hello, my dear students. Hope everybody is doing good, right? So I think yesterday only we met. Everybody will be doing good, right? Anyways, so good morning, right?
Good morning,
Yes,
sir.
Hamsini, good morning. A special good morning. Every time I get a good morning from you in chat.
Happy
Good.
Teachers' Day, sir.
Happy
Thank you,
Teachers' Day.
thank you, everybody. Right? You know why are we celebrating Teachers' Day, right? Why are we celebrating Teachers' Day? I mean, on whose memory we are celebrating Teachers' Day?
Sarvepalli
Sarvepalli Radha.
Radhakrishnan.
What?
Sarvepalli Radhakrishnan's.
Yeah. Okay. Correct. Right. Anyways, so it's just a tribute to that personality. So yeah. Anyways, so I think we can start right away, and I have an important information to be given to you. I guess today's class will be only for 1 hour. Okay, and you will have another hour of class at the evening, 5:30 to 6:30. Okay, why like this? Is because I'm not able to speak continuously. Yesterday you would have seen I was coughing so much. Today it is a little better. I don't want to stress myself. Okay, so now you will have 1 hour class, 11:30 to 12:30. Then again you'll have a class at 5:30 to 6:30. Is it fine, guys?
Okay, sir.
Right? And like I heard that your midterm exams are coming up. I don't know the exact date. 9th, is it? Is it 9th?
Starting from 9th.
Starting from 9th. Okay. So in that case, I would be requiring extra classes, right? So we will have some weekdays also, we'll have some classes. Okay. We'll plan properly because I need to complete your what is the chemical bonding, and I have to complete redox reactions. I think both of them are both the chapters are there for your midterm exams. Okay, redox reaction is very simple. Like it will take only maybe 2 or 3 classes. But chemical bonding again, I'll need another say 2 or 3 classes for me to complete chemical bonding. Okay, so hope you all will cooperate, right? So today it will be one. Now it will be 1 hour. Again in the evening 1 hour, and then in some weekdays you will have classes. Okay, so we'll complete it. It's all for your own good. Like if you don't want, obviously portions will not be completed, right? So that's the point. Anyways, so we'll plan properly and I'll let you know. Like the management will let you know. Epsilon Academy will let you know what are the days, what are the timings, and all that. Right? All those things will come to you. Right? Okay, we have enough people. We have I think 11 people with us. We'll start right away. Let me share my screen. Oh, what is this? Something. Some ad. Right. Okay. Okay, not this. Sorry, this was for 10th. 11th. We'll continue. Yeah, any questions?
Sir, I joined just now, so I didn't know what was happening.
Oh, nothing. Everybody was wishing me for Teachers' Day, and then I gave you
sir.
one.
Happy Teachers' Day.
Yeah. Okay, thank you. So I was telling that we'll have 1 hour class now, only 1 hour class now, 11:30 to 12:30, and you'll have another class today in the evening by 5:30 to 6:30. Because I'm not feeling that good. I don't want to stress myself currently speaking for 1.5 hours. So that's why I split, so that you'll get one half an hour extra also. Right? So you'll have a class now, 11:30 to 12:30, and you'll have another class at 5:30 to 6:30 today. And since portion has to be completed, you will have some extra classes coming in the weekdays also, other than the Saturdays and Sundays next week. So since your midterm exams are coming up, I have to complete redox reactions also. So that will be completed very soon. That is what I was telling. Okay.
Yes, sir. Thank you.
Right, good. So guys, we were seeing the number of examples of how to do this hybridization and stuff. We will just take 2 more examples. As you said that it is going to be only MCQs. Obviously this kind of diagrams, you're never going to write it, right? But I'm sorry, but still it is a very good thing to know, right? How do you write it? How do you represent a sigma bond in hybridization? How do you represent a pi bond? How do you represent a lone pair, right? All these things are important. Right, so we'll just take 2-3 more examples, okay, and then we will see how the hybridization diagram is done, right, and then we'll move on, right? Okay, so today let me start with your famous example H2O. Okay, right, fine. Guys, I'll give you a minute, right? Do it. Can you tell me like say first? Okay, let me go step by step. First thing, what is the steric number here? what is the steric number here? Steric number formula, hope you all remember. It is number
4.
of,
4.
yeah, 4, absolutely. Bonding atoms plus lone pairs, right? Now you see oxygen is the central atom, right? Oxygen is the central atom. And obviously there are 2 hydrogen atoms, so 2 bonding atoms, right? And if you check the Lewis dot structure for oxygen, you'll find that oxygen is having 2 lone pairs. Okay, oxygen is having 2 lone pairs. So 2 plus 2 becomes 4. Fine. So steric number is 4 hybridization.
sp3.
Yes, right. It is going to be sp3. So let us check. Now in this case, I obviously understand that there is only sigma bonds, 2 sigma bonds I have to account for, and 2 lone pairs also I have to account for. There are no pi bonds here, right? So that means after the hybridization is done, you will not find any unpaired electrons because there are no pi bonds here, right? So you have to account for only 2 sigma bonds and 2 lone pairs. Let me do how is it done. Say oxygen is having 1s2, 2s2, 2p4, atomic number 8, right? 1s2, 2s2, 2p4. Now if I look at the ground state, 1, 2, 3, 4. Okay, hope you all remember Hund's rule of maximum multiplicity. 4 electrons should be filled like this only, right? Okay, now this is in ground state, people. Now when I go to excited state, right? So when I go to excited state, now, okay, first things first, you try to shift the electrons, but there is no space, there is no 2D here. 2D is not there because principal quantum number is 2. There is no 2D, right? So all you can do is just shift the electron to the, say I will shift this electron here and say this electron here. Let me see what happens, right? So now if I do that, this is my 2s, this is my 2p. Same way, this is my 2s and this is my 2p. So you'll find that there are already 1 electron here. Now I have shifted this electron here, so that will become 2, and another electron here, 2. This becomes 2.
Sir?
Yeah.
So now lone pair will also come in 2p.
Exactly. Now what you have to remember is lone pair should be placed in the hybridized orbital. HO is hybridized orbital, right? Now we look at what is the hybridization now. Hybridization is sp1, p2, p3, sp3 full. Now I'll have 4 sp3 hybridized orbitals. All are sp3, 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 and sp3. Right now, 2 of the orbitals are having single electron. You can look at this 1, 2, 1, 2, right? But the other 2, you are seeing that there are lone pairs present. Right, oxygen is having 2 lone pairs. We have accounted for 2 lone pairs now, right? Obviously, now these 2 are the one which are going to involve in the sigma bond formation. Obviously, with hydrogen, right? Hydrogen, 2 hydrogens are there. 1 hydrogen, 1 electron, another hydrogen, another electron. 2 sigma bonds overlap. And obviously, other than that, you have still 2 more lone pairs.
Sir?
Yeah.
Sir, but hydrogen doesn't have p orbital, right?
Correct. So
that won't affect, like it can still give electron to sp3.
yeah, if it is, see, it's all about sigma bond, right? When I have sigma bond, I can have an S plus P sigma bond. I told you how it will happen, right? Head-on collision, something like this, right? So this is exactly what happens here. Hydrogen S and oxygen is P, or I don't know, it depends. I would say in this case, it is not P, it is the sp3 hybridized orbital of oxygen and the s orbital of hydrogen will overlap. This is not the shape, but I hope you understand. The overlap is going to happen like this, right? I can even have P and P, right? One P, another P, head-on overlap. Again, I can have a P sigma bond. That is also possible, but in this case, it is not possible because hydrogen, as you said, doesn't have a P orbital. Yes, okay.
Understood, sir.
Right. Okay. Now, one more example, people. Quickly, we'll take another example.
Where did you place the lone pair actually?
Sorry.
Where did you place the lone pair in H2?
I have placed the lone pair inside the hybridized orbital. Total is sp3. I have marked entire thing. Sp1, P2, P3. So now 4 orbitals are there, atomic orbitals. So 4 hybrid orbitals, all are sp3s, right? In 4 of the hybrid orbitals, 2 of them are going to contain the lone pair. Right, and another 2 is accounting for the sigma bond. So 2 sigma bonds, 2 lone pairs. That's it. Done. Yes.
Sir, all the orbitals will have 2 electrons, right?
all the, oh yeah, obviously in this case, I'm telling you, this orbital, I'm not marking it. So basically you can, if you mark it, say one more electron will come here, another electron will come here, but these two are
Yes,
coming
sir.
from hydrogen. Yes.
Yes,
Right.
it is.
Right. I didn't mention it there, but yeah, it's understood that it is going to be sigma bond from hydrogen. Yes. Okay. Right. Another example quickly, we'll go to NH3 molecule. Okay. NH3 molecule. Now directly we can see what is the steric number. Quick steric number.
Four.
Yeah, 4, right? So because I have 3 bonding atoms, I have already seen the Lewis dot structure. Nitrogen is going to have a lone pair, right? sp3. So obviously again it is going to be sp3 hybridization, right? Now let me check how it happens. Nitrogen is going to have 1s2, 2s2, 2p3, right? So 2s having 2 electrons, 2p having 3 electrons, right? Now this is your ground state. When I go to excited state, what will happen now? This electron will be shifted to the anywhere. You can shift it anywhere. I'm just to maintain uniformity, I'm shifting into the last p orbital, right? Say 1, 1, 2, 3, 4. Right now the hybridization is sp3, right? Okay, now what and all you have to account for? Obviously, you see that there are 3 NH sigma bonds. Is it not? There are 3 NH sigma bonds, and obviously you have to account for 1 lone pair on nitrogen, right? So now all of them will combine together to form 4 numbers of sp3 hybridized orbitals, right? And say 2 of them will have unpaired electron, this and this. I mean, three of them actually, in 1, 2, 3, right? And another one is going to contain the lone pair. This is my lone pair. In one of the hybridized orbital, I've accounted for the lone pair now. That's it. See, this lone pair is accounted for here in one of the hybridized orbitals. I told you the lone pair should be placed inside the hybridized orbital, right? Now what will happen? I have 3 hydrogen atoms. I'll use some other color maybe, right? Hydrogen atom, hydrogen atom, hydrogen atom. They will overlap to give paired electrons, right? So 3 sigma bonds and 1 lone pair we have accounted for, right? Okay, one last example so that we'll wind up your hybridization diagram. Let me take SO4 2 minus. Again, it will be sp3. I want to go for little bigger things. Let me go for OSF4. Okay, OSF4. Right. Okay. Now here the confusion will come with the central atom. Can you tell me which is the central atom here, people?
Sulfur.
Sulfur. Again, I told you sulfur is the one which is having least electronegativity, or say least ionization enthalpy among oxygen, fluorine, and sulfur in this particular case. Right. So I can blindly say sulfur is the one which is going to have sulfur is the one which is going to be the central atom. Right. So we have to do the orbital diagram for sulfur only. Right. So sulfur, right, is going to have 1s2, 2s2, 2p6, 3s2, 3p4. Can I continue? Writing something here. What should I write here after this? What should I write here, people? After this?
3d0.
3d0. Now last time I didn't write. Nitrogen doesn't have, oxygen doesn't have, but sulfur has 3d. But it is empty. Right? 3p4 is there. 3d orbital is there, but there are no electrons in 3d. This you'll use for shifting, right? Fine. Again, you have to take only the valence shell. So 3s, 2 electrons, 3p, 4 electrons, and obviously 3d, 5 electrons, no electrons. Okay. Now all you have to do is just shift the electrons here and here. So now when I go to sulfur's excited state, and this is my 3s, 3p, and 3d, say 1 electron here, 3 electrons here, and at last in D you will have 2 electrons because this electron and this electron is shifted. Now actually I forgot to do one thing. We'll find the steric number. I will come back to this. What is the hybridization? Accordingly, I'll be able to do this. Okay. Now you might find difficulty, people, right, for finding this. First you can draw the Lewis dot structure if you are okay, right? If you're okay,
4 single bonds and 1 double bond.
Correct. So we already know fluorine will form only single bonds because its valency is 1. And obviously oxygen atom, not O minus, oxygen atom, if it is there, I know it is going to form a double bond. Right, double bond with sulfur. Right, now sulfur has 6 valence electrons. It belongs to oxygen family. Same number of valence electrons. 6 electrons are there in the valence shell. Out of this, 2 electrons are going to oxygen because double bond is there, right? And 4 electrons are going to go to 4 fluorine atoms and 4 single bonds, right? So now, do I have any lone pair now?
No, sir.
No lone pair, right? 6 electrons are accounted for. No lone pairs, right? Now tell me what is the steric number then for this particular molecule? 5, right? Is it not? 1 oxygen atom and 4 fluorine atoms, totally 5. Steric number 5, hybridization.
sp3d.
sp3d. S1 3 plus 1 4 plus 1 5, totally 5. Yes, sp3d. Right. Okay. Now I'll just I know there is a double bond, right? I know there is a double bond. So now what I have to account for is 5 sigma bonds. Is it not? Basically 1 sigma bond between S and oxygen and 4 SF sigma bonds. And I have to account for 1 pi bond. Is it not? That is between S and oxygen. There's a double bond between S and oxygen, sulfur and oxygen. One of them is a sigma bond, another is a pi bond. So all you have to account for is 5 sigma bonds and 1 pi bond. Oh, that is what you need to do. Right. So we know what is the hybridization here, people. Hybridization, we just now found out it is going to be sp3d, right? S, p1, p2, p3, d1. That's it. Right. How many such orbitals now? 1, 2, 3, 4, 5. All of them are sp3d hybridized orbitals. Right. Now you will have 1 electron, 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 electron. Right. I'll use some other color. Say in this case, fluorine is going to come. 4 fluorines are there, right? And 1 oxygen atom. Now all of them are going to form sigma bonds. So I have accounted for 5 sigma bonds, right? And obviously after the hybridization, you see there is this unpaired electron. That is my SO pi bond. Very simple. Okay, right? So now you understood, right? You must be in your fingertips. After hybridization, how many ever unpaired electron, that many pi bonds, and how many ever hybridized orbitals are there, right? That many sigma bonds. But if you have a lone pair, that lone pair will occupy. How many ever lone pairs are there? That many hybridized orbitals will be occupied by the lone pairs. If you have 1 lone pair, 1 hybridized orbital. If you have 2 lone pairs, 2 hybridized orbitals. Okay, people, right? So now we saw enough examples for you to, even though it's not going to be asked, right? But it's a very good thing to know. If you learn a theory, if you learn something, you must learn thoroughly, right? Okay, fine. Now we understood, right? So now what we'll do is, now we understood all the theory of hybridization. I would say theory of hybridization is over, right? Now all you have to concentrate on is my VSEPR, right? The shapes of the molecules. Right. So I think we made okay, we made a table, right?
Yes, sir.
Where is it? Where is it? Where is it? Where is it? Here. Right. We already accounted for steric number 2, and I told you the only possibility is AB2 type of molecules, say BeCl2, CO2, C2H2. All these are examples, right? And obviously, okay. Now what we'll do is, people, before we move on to see that, let me tell you the difference between a shape and a geometry. Right? Let me tell you the difference between a shape and a geometry. Right? Now, please understand, geometry, I would say geometry is constant for a particular hybridization. Right? Particular hybridization, irrespective of whether I have a lone pair or not. Remember this. Okay. For a, say if I take sp2 hybridization, right? I know sp2 hybridization can have two types of forms. One is, okay, AB3, sp2 will have, or I can have AB2L. Right now, whether I have, now this is, both of them are going to have sp2 hybridization. Okay, right now now if both of them have sp2 hybridization, it really doesn't matter in which of the form I have lone pair or not. By the moment I see hybridization, I can fix the geometry. Okay, by the moment I see hybridization, I can fix the geometry of the molecule.
Sir.
Okay, then what is shape? Right, let me tell you what is shape. Then shape, I would define it as, it is the consequence, or okay, I'll write like this: it's a result of presence of lone pair in the geometry. Right, I would say, one second, let me complete this. Shape comes from VSEPR. Basically, for shape only we have to use VSEPR, the electron repulsion and stuff. We already know what is VSEPR, right? But for geometry, there is no VSEPR. It does not take into account of VSEPR. There is no bond pair bond. Like obviously it has, but not so intuitively. Okay, so what you have to understand is shape comes from VSEPR. You have to look into the lone pairs. Right, and if you have lone pair, obviously now the same example I take AB2, I mean AB3 and AB3L, right? Now this, both of them will have same geometry. I would say the geometry in this case, I can tell the geometry in this case. I'll tell you how this comes, right? The geometry is trigonal planar for both of them. The geometry, again I repeat, geometry is same irrespective of whether you have a lone pair or not. Once you know the hybridization, it's fixed, right? But shape, as I told you, is a result of presence of lone pair in the geometry. In the geometry, if you have a lone pair, then obviously there is going to be some difference in the shape, right? For example, AB3 will again be trigonal planar. I'm talking about the shape now, right? But AB3, oh no, not AB3L, AB2L, sorry, right? Strike number 3, not AB3L, AB2L, right? So AB2L will have a bent shape, or we call it as V-shaped molecule. Okay, hope you're all able to get the difference between what is geometry and what is shape. For shape, we take into account the presence of lone pair, right? But in case of geometry, whether it's a bonding atom or whether it's a lone pair, we give same treatment. Whether it's a bonding electron or a lone pair of electron, we give same treatment, but in shape, we give different treatment for bond pairs and lone pairs. Yes, someone was asking a question. Yes?
No, sir, now I got it, sir. Now that you explained it.
Got it? Okay, good.
Sir?
Right? Yeah, tell me.
So geometry is equal to the shape when number of lone pair is 0.
I was about to tell that point. Good point. Good point to note. Shape is equal to geometry if no lone pair is there, in no lone pair in central atom. Okay, the geometry will be equal to the shape if obviously there are no lone pairs, because it's understood, right? You can see here both these molecules AB2 and AB3L is having a trigonal planar geometry. Now you look at AB3, it doesn't have a lone pair, so the geometry of AB2, I mean, anyways, you understand, if there is no lone pair, the geometry and shape becomes equal. But if there is a lone pair, you see that the shape is changing. Okay, this is a good thing to note, right? Okay, now what we'll try to understand is how is it that AB3 is having a shape called as trigonal planar, or say how the geometry is trigonal planar, however you want to see, right? Now all you have to understand is VSEPR, right? So in AB3, I have 3 bond pairs, 3 bonding pairs of electrons I have, right? Bonding pairs of electrons I have. So what should I do? I have to make sure that the repulsions between the bond pair of electrons are minimum. That is what VSEPR says. And the structure should be in such a way that the repulsions between these bonding pair of electrons should be minimum. Right? Now, how will I make it minimum? Obviously, by increasing the distance between the bonding pair of electrons. Maximum distance, minimum repulsion. right? Now, the only way you will be able to achieve that if the bonding atoms are like this, right? It's going to be a triangle in the same plane, or in the board of the laptop, or in the board of the sorry, in the plane of the your screen, laptop screen or phone screen, whatever it is, right? So now you see the bond angle here would be, what will be the bond?
120.
120 degree. Again, this bond angle will be 120. This bond angle will be 120. Okay, so this shape, right, is what is called as trigonal planar shape or trigonal planar geometry. Okay, right, fine. Now this we understood. Now obviously BF3 will come into this trigonal planar, right? But the moment you have a lone pair, say for example, you had NO2 minus, right? Yeah, NO2 minus molecule, right? This belongs to the category AB2L because I know nitrogen has a lone pair. We already saw the example, right? Now what happens? Now if the geometry is same, geometry you write like this, and one double bond O, one single bond O minus, and there is a lone pair. This is the geometry. Geometry is again trigonal planar. Geometry is trigonal planar, right? But when I go to shapes, right, now you have to take the consequence of this, right? Now remember, in shape, you will not represent the lone pair. Again, one more point you can add to the shape. In shape, don't include lone pair, right? But the effect of lone pair is included. Effect of lone pair is included, but you will not show the lone pair. That's what I'm telling you, right? In the shape, you will not show the lone pair at all.
Like
right?
the dots, sir.
Yeah, exactly. This,
Okay.
this dot, what we wrote here is geometry. Whenever you represent the lone pair, you always represent it like this. You put this thing and you put two dots. That means in this orbital, there is this lone pair present. This is my geometry. But same thing, I do it for shape, right? Now, what do you think is going to happen? This bond angle, right? Okay, if this was a bonding atom, if this was not a lone pair, right? If this was not a lone pair, like in the case of BF3, obviously the bond angle would have been 120, right? Now, what is going to happen? I had only bond pair repulsions here. The previous case, I had only bond pair repulsions, right? In this case, you will have lone pair repulsion as well as bond pair repulsion. Is it not? This lone pair can have a lone pair repulsion between these two. I can have a lone pair repulsion between these two, and bond pair repulsion between these two. Is it not? Now, I have to make sure that all of them are minimum according to VSEPR for me to get the shape, right? So what should I do is, obviously I know lone pair repulsion is greater than the bond pair repulsion. So the first priority has to be given to lone pair repulsion only, right? So now what is going to happen? I am going to have repulsion between these two and these two, right? So now what is going to happen is this oxygen is going to come far away from the lone pair, and this oxygen will also try to come far away from the lone pair to reduce the repulsion. Now you can ask me, sir, if they come closer, the bond pair repulsion will increase, but that is not the priority here. The priority is reducing this, not this. Again, I repeat. So now to reduce the lone pair repulsion, what is going to happen is this oxygen will come this side away from the lone pair, and this oxygen also try to come away from the lone pair to minimize the lone pair repulsion. Now the question is, sir, this will increase, right? The bond pair, the repulsion between these two will increase, right? But that is not the priority. The priority is this. Okay, now this is the consequence. The consequence, the result is that the oxygen atoms are moving away from the lone pair. So if they move away from the lone pair, they will have something like this. Is it not? And remember, this bond angle theta is not equal to 120. Actually, theta will be lesser than 120 degrees. Is it not? If these two are very far away, obviously I can say that the bond angle is 120. Now, if these two come closer, what is happening? The bond angle is reducing, right? Right? The bond constricts. So now this angle which we have is definitely not 120. it is going to be less than 120. We don't know the exact angle. We can measure it with the help of sophisticated instruments, but the exact value is not important for us. All you have to understand is this bond angle will be lesser than 120, right? And you see the shape is very simple, right? You can see how the shape is. This shape is what is called as bent, or it is what is called as your V shape. You can see it's V shape. Now you see, I did not represent the lone pair here. I did not. In shape, you do not represent the lone pair. But in geometry, you see the same NO2 minus. Yeah, I'll write it again in this case. Say I have a lone pair, this thing, and O minus. This is my geometry, trigonal planar. Right? I represent the lone pair. But in the geometry, I see I have just represented the bonding atoms and just, what is the shape? That is the bent shape. There is no requirement of representing the lone pair here. But the effect of lone pair, yes, that is included. Hope you're all able to get the point. Right? So now we'll go to the table and we'll fill it. There's a table. Yeah, right. So table, I told you where when I have steric number 3, you can even write the hybridization here, sp2. Right? So both of them will have sp2. The geometry of AB3 will be again what? Trigonal planar. Right? Obviously geometry, irrespective of whether I have a lone pair or not, it is going to be same. Trigonal planar only for AB2L also. Right? But the shape of this is trigonal planar. But here the shape of AB2L will be different. That is your V-shaped or bent shape, I call it. Right? Shape is also filled. And for trigonal planar, I know the bond angle is 120 degree, right? And here it is going to be less than 120. That's all you understand. Right? An example for AB3 is BF3. An example for AB2L is NO2 minus. So the example. Any questions anybody has? Everything is clear?
Sir, 2 lone pairs and 1 bond pair is not possible.
Possible, not possible, not possible. No. Okay, you're asking about a case where I can have ABL2, right? No,
Yes,
not
sir.
possible. This is not possible. What happened? Right, okay, fine. Now we'll move on to steric number 4 and
Sir?
we'll see what happens. Yeah, any questions?
These are the only 3 types of bond pairs that can happen. Not bond pair.
For steric number 3, only 2 possibilities. For
Oh, okay.
steric number 2, only 1 possibility.
Oh, so there are more.
Okay. Yeah, there are more. When I go to steric number 4, 5, 6, 7, until 7, I can go. And you'll see that the possibility of AB3, something like that, will also increase. We'll see one by one. Don't worry.
Okay, sir.
Okay, right. Now we'll take steric number 4, people. Let me use that board here only because I don't want to move so much, right? So if I have 4, I know the hybridization is sp3. Correct, right? Now the first case we'll take is where I have no lone pair, AB4 type of molecule. Obviously, 4 bonding atoms means 4 lone pairs. And the example I can take is so many examples I have, say SO4 2 minus, you will see that there are no lone pairs on sulfur. We saw another example, NH4 plus, right? NH4 plus again doesn't have a lone. I already know the shape, right? I already know the Lewis dot structure. It doesn't have any lone pair. Again, SO4 2 minus doesn't have any lone pair. All of them will basically be sp3 hybridized without any lone pair, right? Okay. Now, or best, how can I forget CH4? All alkenes, CH4, C2H6, C3H8, all of them will come to this category, right? 4 bonding atoms and no lone pair. How C2H6 comes? Very simple. I write CH3, CH3. Now you see, for this carbon, 3 hydrogens, 1 carbon, 4 bonding atoms. Same way, for this carbon, 3 hydrogens, 1 carbon, again 4 bonding atoms. Okay, so I would say both these carbon atoms are sp3 hybridized. Right? No issues. Now all of them come under one category because all of them are AB4 type. That means they don't have any lone pair on them and all of them are sp3 hybridized. Central atom, obviously. Right. Now let us move on to see how the shape and in this case, the shape and geometry is same, right? Because there's no lone pair. Right. Now how the shape, this is how the shape is. For AB4, the shape is going to look like this. A, B, another B, and B. Okay. Now, what does this represent? These are the normal bonds. Okay. So now if I draw a normal line, these two indicates that these bonds are in the plane, in the sense in the board of the laptop screen, or in the plane of the phone screen you're looking into, right? But this wedge, this is what is called as a wedge, right? This wedge represents that the bond is coming towards you. Okay, or if I talk with respect to me, it is coming towards me from the laptop, right? If you're going to talk with respect to you, it is coming towards you. Okay, like this, right? This is the plane of the molecule. So the bond is going to come like this inside, z-axis, something like that, right? It's coming towards you. So wedge represents the bond is coming towards you. Okay, right. Now what this dashed line represents, this is what is called, we can call it as a dashed line or dashed line. Now this indicates that the bond is going away from you, in the sense that, say, if I talk with respect to me, right, the bond is going away from me. It's pointing like this. Other bond was pointing towards me, right? Now this time it is pointing away from you. Like if I can tell, it is pointing away from you. Okay, right? Now, I think if you're able to easily understand, take the example of a tripod stand, right? Tripod stand, I don't know, have you been to a lab and seen a tripod stand? I don't know whether you're able to understand what I'm saying. There is something called as a tripod stand. Have you seen?
Yes, sir.
It'll
Right? Or I don't know, tripod stand, if I have to give you another example, any camera stand like people use for DSLRs and all that, right? They stand, say it's like a 1, 2, 3, the three kind of vertical lines will come, right? Now that is the perfect example you can take, right? Say 3, like that's exactly what is represented here. This is one of the lines, second line, third line. Obviously the fourth one will be in the same plane of this. Okay, now this particular shape or geometry is what is called as tetrahedral.
Sir,
Yeah,
sir, in tripod stand only one will come out of the plane, right?
yeah, like obviously the top one is missing, but I'm
Yes,
just making you understand how the bonds can be. That's what I'm trying.
But here both the dashed line as well as wedge are outside the plane.
No. See, wait. How can I show it? Okay, something I'll do.
Sir, you can
Right.
Google it.
But no, not required. I can show it now like this one. Right. Now you look at this. Okay. Now, actually, it is not perfect, but what you have to understand, say this pen, right, is coming towards you. Okay. This pen is coming towards you, and this black pen, what you see, is going away from you, right? And this is in the same plane. Are you able to get what I'm saying? Yes. This is not a perfect shape.
Sir, then where is the fourth pen?
Fourth one is in the same plane. Like say, if I consider this as one plane, it is going to be in the same plane as this. Are you able to get?
Yes, sir, understood.
Okay, say now another one will be like this. I have to hold it, and another one will be like this. This and this are in the same plane. This is going away from you, and this is coming towards you. Yes, okay.
Yes, sir.
Okay, good.
Sir,
good.
wedge is the one which comes towards.
Yeah, wedge is the one. The shaded line is what is coming towards you. The dashed line is going away from you.
Okay, sir. Got it.
Right?
Sir,
Yeah.
sir, but the bond angle between wedge and the dashed line is not exactly 180 degree.
It is not 180. Who said it's 180? I'm coming to the bond angle. I'm coming. Right? It is not 180. It is, I'll tell you the bond angle.
I said
Right, so
109.5.
Yeah, correct. 109 degree, 5 minutes. Right? Anyways, now the shape, this kind of shape is what is called as tetrahedral shape. Very, very important. right? And the bond angles here, all bond angles are same, right? All the bond angles are same. The bond angle is 109 degree, 5 minutes. Okay, 109 degree, 5 minutes is what is the bond angle, right? Okay, so now I can fill the table here. Where is the table? For AB4, I told the geometry is tetrahedral. The shape is same because there is no lone pair. And the bond angle I mentioned as 109 degree, 5 minutes. And there are so many examples. CH4, SO4 2 minus, NH4 plus. So many examples are there for tetrahedral molecules. Okay.
So then what is the shape?
Shape is same, right? Because there is no
Okay,
lone
sir.
pair, right? When I don't have lone pair, geometry and shape are same. Shape is also tetrahedral only. Okay, right, good. Now we'll
So-
move on to, yeah, tell me.
Sir, if the bond angle is 109 degree 5 minutes, then they are not exactly like towards and away from us, right? The wedge and the dash line.
Why is it, say I just take one of the case, say it's like this, right? Now, obviously, if you check properly, this is in the same plane. I have to do something like this, right? Now, obviously, you see this bond angle will be 109. This bond angle will be 109. And this is not exactly proper, but this will be 109 if you measure properly. If you look at the 3D structure, it will be 109.
Yes, sir, but how are they towards and away from us?
See, for angle, I can see, I just need two lines for an angle to be constructed. Whether the lines are in same plane or in different planes doesn't matter, right? Mathematically, right? Say
Yes,
I can have one line like this. I can have another line like this. I can still have an angle. I can have in the same plane. Again, I can have an angle. If it is in this plane also, I can have an angle, right? Are you able
Yes,
to get
sir.
the point? Right. Okay, good. Right. So now we understood that the shape and geometry are tetrahedral and the bond angle is 109 degree 5 minutes. Right. Now we'll move on. We'll move on to the case where I have a lone pair. Say same steric number 4 only, right? But let me take the example as AB3L. That is 3 bonding atoms and 1 lone pair. Okay, 3 bonding atoms and 1 lone pair. Again, steric number 4, sp3 hybridization. Right. Now can you tell me what will be the geometry here? Tetrahedral. That's it. Once you know the hybridization, that's it. You know the geometry. Blindly, you can say. Only the shape is going to be different. Right. Now, the famous example we can take for this is your NH3 molecule. Is it not? 3 bonding atoms, and I know I have a lone pair here. Okay, 3 bonding atoms and 1 lone pair I have. Okay. Now, what you have to do, obviously, if I draw the geometry, again, I expect it to be tetrahedral. Right, I expect it to be tetrahedral. This is the geometry. Tetrahedral. Right, but when I look at the shape, obviously now what is going to happen? There'll be a bond pair, lone pair, repulsion between this and this, between this and this, and between this and this bond. Okay, so what is going to happen is that the shape is going to come out like this. Again, I will not represent the lone pair in the shape, right? This is the shape. Okay, now this shape is what is called as a pyramidal shape. Right, it's like a pyramid. I think I can understand what I'm trying to say. Obviously,
Yes,
now
yes.
what happened here is that this bond angle, if this was a bonding atom, the bond angle would have been 109 degree 5 minutes, but it is not going to be because all the bonds are coming closer. All the 3 bonds are coming closer like this. Okay, so the bond angle here, say I say theta, right? Now that theta will be lesser than 109 degree 5 minutes for sure. That I can say. Again, because the dominating repulsion is between the lone pair and bond pair. So we do not give our priority to your bond pair repulsions. Okay, so this shape is what is called as your pyramidal shape. From the name itself, it's like a pyramid. Is it not? Like a pyramidal shape, right? Fine. So now I can fill the table here. I think it's very clumsy. Let me, where will I write it? Yeah, tell me. Yes.
Sir, actually pyramidal means regular pyramidal has 4 faces, right? Here I guess only 3 faces.
Good, good, good. Yes, this is called trigonal pyramidal shape. Okay, the exact name is called trigonal pyramidal shape. This is like a trigonal pyramid. Three lines pyramid. Okay, there is one more pyramidal shape that there are different pyramidal shapes you'll come across. This one is trigonal pyramidal shape. Okay, the quite good question actually. But we generally say it's only pyramidal because when I say pyramidal, it is by default it is trigonal pyramidal. Okay, right. So now people, I can fill this here. Let me rub certain things. Okay, so now I know for AB3L, I'm sorry, for AB3L, the geometry is tetrahedral, and just now we mentioned that the shape is trigonal pyramidal, right? And the bond angle is less than 109 degree 5 minutes, right? And obviously for them, the example is NH3, right? Any other example can you think of for this kind of type? Three bond pairs and one lone pair. Anything you can think of? Any ions can you think of? No. Actually, that will not work. I am thinking of something. Guys, what about hydronium ion H3O plus? What category it belongs to? What category does it belong to, people? H3O plus. Now, positive charge goes to which atom now? Tell me. Oxygen or hydrogen? According to hybridization, obviously. According to hybridization. Positive charge goes to?
Positive will go to central atom.
Positive will go to central atom. So obviously positive in this case will go to oxygen. Is it not? Right. So now let me check. For oxygen, now I have, instead of 4 unpaired electrons, instead of 6 electrons in the valence shell, I'm going to have only 5 electrons now. Is it not? Because it is oxygen plus. Right. So now I'll have only 5 electrons. 1, 2, 3, 4, 5. Because it's oxygen plus. And I have 3 hydrogen atoms. Right. So hydrogen atoms will take 1, 1, and 1. Right. Obviously, now all the whatever is given will be taken. Right. So what do you see? Again, there is a one lone pair on oxygen. So can I say this also belongs to AB3L? Yes or no? No. Yes. Did you understand, people? H3O plus again belongs to AB3L because there are 3 hydrogen atoms, and you will find that there is a lone pair on oxygen because it's oxygen plus. Do you get the point? Yes, no?
Sir, could you repeat, sir?
What happened?
Could you repeat, sir?
Yeah, sure. What I'm telling is, I'm taking the example as H3O plus. Right. So we are talking about a case where I can have AB3L type of molecule. One of the example we saw was NH3 because it has a lone pair here. Right. Now you see oxygen is also going to have a lone pair. Right. So what is the steric number here? 3 hydrogen atoms, 3 and plus 1 lone pair on oxygen. Again, it is 4, sp3 hybridized, but still it belongs to AB3L type of molecule only, just like NH3. How it is like this? Now, oxygen is going to have a positive charge. So oxygen should have had 6 electrons, but now I have only 5 electrons in oxygen valence shell. No, I'm not putting 6. You see, I'm putting only 5. Hydrogens, 3 hydrogens are there. Right? So hydrogen will take up this electron, and this electron, and whatever was given will be taken. Done. So now if I write the structure, again, you see hydrogen, 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 and there is a lone pair on oxygen with obviously a positive charge on oxygen. Yes. So does it not belong to A, B1, B2, B3, and one lone pair? Yes. Now understood?
Yes, sir. Got it.
Yes, sir.
Okay, right. Very simple now. So NH3, H3O plus, all these belongs to the same category. Hydronium ion, we call it. Right. So AB3L will have
what
tetrahedral
about-
one second, tetrahedral geometry, trigonal pyramidal shape, and the bond angle will be less than 109 degree 5 minutes. And the examples are NH3 and H3O plus. Yes, the question?
SO4 2 minus.
SO4 2 minus. Okay, we'll check whether SO4 2 minus comes under this category. SO4 2 minus actually comes under the tetrahedral category, that is AB4 category. Let me tell you how. Draw the Lewis-Dot structure, no, please. Everybody, we already have done this, but still draw the Lewis-Dot structure for SO4 2 minus. I'll give you a minute's time. Quickly draw.
Sir, I have a doubt, sir.
Yeah, tell me.
Sir, so in SO4, like if it didn't have any charge, so there are four oxygen molecules. But now since it is 2 minus, 2 of them will have O minus and 2 of them will be elemental.
Correct.
So two double bonds and 2 single bonds.
Absolutely, yes, correct. So there are no lone pairs because sulfur is having 6 valence electrons, 2 double bonds, 4 electrons are gone, 2 single bonds, 2 electrons are gone. Done. Right? So anyways, for you to confirm this, let me draw the Lewis-Dot structure, people. Sulfur is having 6 valence electrons, 1, 2, 3, 4, 5, 6. And in SO4 2 minus, this 2 minus means 2 O minuses are there and 2 oxygen atom is there. Okay, we have already spoken about this, how you go to the charges. Again, negative charge and bonding atom, positive charge central atom. In this case, negative goes to oxygen. Right. Now, say oxygen is going to have, say O minus we will take first. O minus will have 7 electrons in the valence shell, right? 1, 2, 3, 4, 5, 6, 7. Same way here also. This is 1, 2, 3, 4, 5, 6, 7. And 2 oxygen atoms will have 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right now, this oxygen requires only 1 electron to satisfy its octet. Same way, this O minus requires only 1 electron to satisfy its octet, and this oxygen atom requires 2 electrons, and this oxygen atom requires 2 electrons. So now, whatever was given by sulfur will be taken back. Taken also. So you see, this is how the structure is. Do I find any lone pair? These 2 are bonded. These 2 are bonded. These 2 are bonded. These 2 are bonded. And these 2 are bonded. Right? Basically, the structure will look like this. Double bond, O minus, O minus. This is exactly how it looks. There is no lone pair on sulfur. Right? So it belongs to the category AB4 only. There is no lone pair on sulfur. Yes? Understood? Whomever asked this SO4 2 minus?
Yes, sir.
Right? Okay, good. Right, so guys, the table is becoming so clumsy. Let me make another table. So till now it's done, right? You just continue in the same table as you continue, right? We completed till AB3L, right? Okay, now we continue the same hybridization only, that is sp3, but different. Okay, say it is steric number. Oh, what happened? Suddenly something came. Okay. Let me mark it here. So steric number, type, or we can even have hybridization, but steric number of the hybridization is done. So steric number, type, geometry, shape, bond angle, BA, and examples. Right. So now one more types, again steric number 4, sp3 hybridization only. Right. Now we'll take the example of AB2L2. Again, still steric number 4 only, but in this case, 2 bonding atoms and two lone pairs. Give me an example quickly. Example. We saw it today.
H2O, sir.
Correct. Right. H2O, you see, oxygen is having 2 lone pairs and 2 bonding atoms, that is 2 hydrogen atoms. Right. So directly I can give the example as H2O, H2S. All these will have same kind of geometry and shape. Right. Okay. Geometry. What is the geometry of AB2L2 people? I know the hybridization. So what is the geometry?
Same, sir.
Same means what?
Trigonal.
Tetrahedral.
Oh, sorry,
The moment I know the geometry, the moment I know the hybridization, I know the geometry. That is done. Right? So now, if I have to bring in the shapes, now this is how we'll do it. Again, what will you understand is that in this is the first time that there is going to be lone pair repulsion present. Is it not? Because there are 2 lone pairs.
Yes.
This is the first time you will find that lone pair repulsion is there, right? So now, if you include that oxygen, now I have to make sure that the lone pairs are very, very far away from each other. Say maximum distance apart, I put them, right? Now, if they are little going away from each other, now obviously I have 2 more bonding atoms also, right? I have 2 more bonding atoms also. Now, when they try to go far away from each other, these 2 will come closer. Is it not? So obviously this will increase, and obviously they will also try to move away from the lone pair. So the lone pairs from each other will try to move away, and the bond pairs will also try to move away from the lone pairs. 2 things are happening here. Again, I repeat, 2 lone pairs will try to move away from each other because I want to reduce lone pair repulsion. First priority. Second priority is that the hydrogen atoms will also try to move away from the lone pairs because I want to reduce the bond pair lone pair repulsion. Right? Obviously, the least priority goes to bond pair. That you cannot do anything with this because that repulsion will definitely be there. You cannot reduce it further. Right? So now this is kind of geometry what we write. So if I don't include this, that becomes the shape. Right? O, H, H. That's it. Right? Now, can you tell me what will be the shape here?
Bent.
V-shaped.
Again, it's going to be bent or V-shaped only. Just like I had an NO2 molecule, but that time the number of lone pair is only 1. Here the number of lone pair is 2. That's the only difference here. Okay, right? Now here the shape is going to be V-shaped or it is bent shaped. And the bond angle, we don't have to look into this. A bond angle will definitely be less than 109 degree 5 minutes. No doubt about it. Okay. And I would say the bond angle is going to be lesser than in the case of ammonia. Ammonia, what happened? There was AB3L, or I can write it like this. The bond angle will be lesser than a case where I have AB2L, definitely, because there I had only 1 lone pair. Only lone pair bond pair repulsions are there. But here, since I have 2 lone pairs, they will try to come far away. By that will bring the lone pair and bond pair closer. So they will still try to move far away, the bond pairs, right? So the bond angle will be very small, right? So definitely it will be lesser than a case where I'm going to have AB2L, NH3, H3O plus, all these things will have little more bond angle than AB2L2. And the examples are obviously H2O, H2S, all these are things. Okay,
Sir?
guys, I think, yeah, tell me.
Sir, xenon tetrafluoride, it looks like AB4, but then it has AB2L2.
AB4L2. It has 2 lone pairs. XCF4, right? If you check, this is going to have 2 more lone pairs. Basically, it has 8 valence electrons. 4 will go to fluorine. 4 more electrons are left for 2 lone pairs. This belongs to AB4L2. That is an entirely different category. Yes? Okay.
Okay, sir.
Right, you will find that this is going to have a shape as square planar. Anyways, you don't have to go look into this. We'll come square planar it is. It is different from tetrahedral anyways, right? Okay, guys, I think it's time, right? 12:30. We'll stop with here today. So again, we'll meet today at 5:30. Is it fine? Any questions? Anybody has any plans that they will not attend, sir? I have this, I have to do that, I'm going out. Anybody has any question, any issues like that? 5:30?
Sir, can you repeat the examples for this type, sir? AB to L2.
L2, AB to L2 example is H2O and H2S.
Okay, sir.
Okay, right. Any other questions anybody has, people? Okay, thank you so much. We'll again meet at 5:30
Sir,
today.
Happy
Yeah, tell me.
Teachers' Day, sir.
Thank you, Girija. Thank you. Right. So today we'll meet at 5:30. Thank you, guys. We'll meet again.
Thank you.
Okay,
Ending
sir.
the class.
Thank
you,
you,
sir.
sir.
Thank you, everybody. Thank you.